In this video, we're going to prove the chain rule for derivatives. So a chain rule is used anytime you have a composition of two functions, f of g of x. And just like all of the other proofs for all of the derivative rules, we're going to use the limit as h approaches 0 of the difference quotient. So I've already got that in here. The limit as h approaches 0 of f of g of x plus h minus f of g of x all over h. And similarly to how we proved the product and the quotient rule by adding and subtracting a single term into the numerator, effectively adding nothing to it, we're going to do something similar, except instead of adding nothing, we're just going to multiply it by 1. And the 1 that we're going to multiply it by is g of x plus h minus g of x over g of x plus h minus g of x. Since anything divided by itself is 1, we can just multiply by that fraction, and it doesn't fundamentally change the limit that we're looking at here. And if we notice, the g of x plus h minus the g of x is the top of a difference quotient to find the derivative of g, and this h is the bottom of the difference quotient. It would also allow us to find a derivative of g if we could move it over to the right-hand side. So we're just going to flip the denominators of these two fractions that are being multiplied by each other around and separate it into two limits using multiplication. So we're still going to have a limit as h approaches 0 of f of g of x plus h minus f of g of x. But instead of it being over h, we're going to move this denominator over here. So it's now over g of x plus h minus g of x. And we're going to multiply that by the limit as h approaches 0 of g of x plus h minus g of x, the same numerator we had, now divided by this h, allowing us to turn this entire right limit into just the derivative of g of x. So this whole thing is just going to become g prime of x. And on the left-hand side, we're kind of left with a little bit of a mess. And one of the things we've learned along the way here is that we can always do a u substitution when we have indeterminate limits that are just kind of a mess. So in this case, the u substitution we're going to use is, let's let, might as well let u equal the denominator, g of x plus h minus g of x. Now, the reason we're doing that specific substitution is because we'd like to turn this whole limit into a difference quotient as well. But in order for it to be a difference quotient, we have to have a single variable in the denominator. And if we let u equal that whole denominator, well, then we've got a single variable in that denominator. So if u is equal to g of x plus h minus g of x, that means two things that are kind of important here. One, that as h approaches 0, u will approach, well, g of x plus 0, or just g of x, minus g of x, which g of x minus g of x is just 0. So instead of a limit as h approaches 0, we're now going to have a limit as u approaches 0. And the other thing it means is that g of x plus h is equal to g of x plus u. And we can see that just by rearranging this expression we wrote for u, just by adding a g of x to the other side. So we're now going to rewrite this limit, substituting in all of the u values and the g of x plus h values and transforming it into a limit as u approaches 0. So we are going to have a limit as u approaches 0. If we look back here, we had f of g of x plus h. And so now instead of having f of g of x plus h, we're going to have f of g of x plus u. And then we're going to continue with the minus f of g of x that we already had. And it's all going to be over u. And that limit is being multiplied by g prime of x, what we already found this second limit to be. And if we look carefully at this new limit, we can see that it is a limit as some variable, u, approaches 0, of f of something plus that u minus f of that same thing, both of those being g of x, all over u. It looks just like a difference quotient, only instead of h, we now have u's in all the places we'd normally have h's, and in all the places we'd normally have an x, instead we have g of x. So this limit is just a difference quotient for f of g of x. So it's the derivative of f evaluated at g of x, f prime of g of x. And then it's f prime of g of x times g prime of x. And that's the chain rule. Chain rule says if you're looking for the derivative of f of g of x, it's the derivative of f evaluated at g of x times the derivative of g. And this will allow us to expand the number of functions that we're able to take the derivative of, because most derivatives require us to use the chain rule.